This is the sixth section of chapter 2 on centers of mass of plane figures, and here we're going to be looking at a lamina in equilibrium. So let's say, for example, we've got a lamina like this, and it's being suspended from a piece of string, and it's not moving, so it's in equilibrium, and it's free to sort of rest like that. Then what we'll always find is that the center of mass is directly below this point of suspension. So if we put center of mass here, that will always be directly below the point at which it's suspended. So just do a dotted line like that. Now if we know whereabouts the center of mass is in relation to one of the corners, then it should be fairly easy then to use some trigonometry to work out, let's say, this angle here, because we can work out this length or distance, we can work out this distance, or we can work out the angle on this side, or the angle that this edge makes with the horizontal. So it's just going to be a bit of trigonometry once we know where the center of mass is. So we'll start by working out the center of mass. We'll draw in this little dotted line here, which is leading directly up to the point that it's suspended, and then we'll use that to work out any angles that we need to find. So when a lamina is freely suspended in equilibrium, the center of mass is always directly below the point of suspension. Let's just add the word in, so that sentence now makes some sense. Example 16. Find the angle that the line AB makes with the vertical if this L-shaped lamina is freely suspended from 3 different points, A, B, and then E. The first thing that we need to do is to calculate the center of mass. So we're going to do a table. Okay, so here's my table. Start with the upper rectangle, which has an area of 8. And the bottom rectangle also has an area of 8. For the upper rectangle up here, its center of mass is going to be 1 across, and then 2 up here, and then another 2 up. So it's going to be 1, 4. So 1 across, 4 up. For the lower rectangle, its center of mass is going to be 2 across and 1 up. So 2, 1. So now we can work out x bar. So that'll be 8 times 1 plus 8 times 2 divided by 8 plus 8. And then y bar, that's going to be 8 times 4 plus 8 times 1 over 8 plus 8. And if we work those out, we'll get 1.5, and for y bar 2.5. So now we're ready to tackle the question. So part A, it's being suspended from point A. So we're going to mark in roughly where the center of mass is. So again, 1.5 across and 2.5 out. So it's roughly in sort of this type of position. It doesn't need to be exact, but we need to get it in the right type of place. So that's where G is. And if it's being suspended from A, now remember this point A is going to be directly below the point that it's suspended. So what we do is we draw a line from G going through the point at which it's suspended. Now this line here is going to be vertical. It's always going to be vertical. So to give you some idea of what it's going to look like, it's going to be something like this. So here's the point A where it's being suspended, B, C, D, E, F, and that's where we've got D and D dash where it's been sort of split up, but it's going to be something like that. And we need to find the angle between that vertical and the side AB, which is this side here. So on my diagram, that's this angle, we'll call it alpha. And all we need to do is to say, right, on the diagram that we've drawn, that angle is between the vertical, that line that we've drawn, and the side that we're trying to find the angle in between. So it's that angle there. So it's just going to be a little bit of trigonometry. If I was to draw the triangle that we're going to use to find the size of that angle, actually it might be useful here just to write down the coordinates of that center of mass. So that's 1.5 2.5. You might need to do a bit of adding and subtracting, but we just want the lengths of these sides. So this side at the bottom, well, that's just 1.5 because we've got the centre of mass from A. We've taken A as our origin. And then the length of this side, that's going to be 2.5 there. So we know that the centre of mass, the angle is going to be the tan inverse of the opposite to that angle, 2.5 divided by 1.5. And that gives us 59.0 if we take it to 3 significant figures. Okay, B. So now it's being suspended from point B. So we'll take off all the things that we've added from before, and the vertical is now going to be in a different position. So we'll take this off, we'll leave the centre of mass on. So we now draw a line from the centre of mass through point B, like this. So the lamina is now going to look something like this. And again, this line here, we just need to imagine as the vertical. If it helps, you can just turn your diagram around so that line is vertical. And we want to find the angle that's here. So we'll draw our triangle on, and then we'll need to work out the lengths so we can work out what that angle is. Okay, so we know that this side is 2.5 because it goes up to 2.5. So I'll put that on there, 2.5. We just need to take a little bit of care with the bottom length here, because we know that it's 1.5 on this side up to here, and we want to know this one. So it's going to be 4 minus 2.5. So this is going to be 2.5 here. So that's 2.5. So that angle is going to be the tan inverse of 2.5 over 2.5, 45 degrees. So we don't really need to work that out, because if it's a right angled isosceles, it's got to be 45 degrees. So that's 45 degrees. Then the last bit, part C, our point of suspension is now E. So we're going to take these off. We don't need these anymore. And we're going to be drawing a line that goes through point E from that point of suspension. So it's going to be something like this. Yeah. So now that becomes my vertical. Again, I'll just draw a little sketch to show you what it would look like. So being suspended, it's going to look something like this. We want to find the angle between AB. So really we've got to extend that down to here, down to the AB, and to find that angle. So let's do that on my diagram. We'll extend that down to here, and we'll just mark down that this is the angle that we're trying to find. Now you can see that you can't find it directly, so we're going to have to use something at the top, but I do notice I've got a Z angle here. So this angle here is also going to be the same as the angle that I want to find. So to do that, I need to find this angle in here. We'll call that theta. So I'm going to draw in my right angle triangle and then work out the lengths to allow me to work out this angle here. So this is where we just need to be careful working at angles. We know that the centre of mass from the bottom goes up 2.5. So if we go up to 2.5, that means that this little bit here is 0.5, meaning the actual length of this side of this right angle triangle is 3.5. So that this is going to be 3.5 here. Then going across, we know that we go across 1.5 to get to our centre of mass. If this whole thing is 2 and we've gone across 1.5, that means that this length here is also 0.5. So this is also 0.5 as well. So I'll just mark that down here, 0.5. So that first angle that I want to find is going to be the tan inverse of 0.5 over 3.5, and I need to subtract that from 90. So it's going to be 90 because obviously that's the one that I want to find. 90 minus the tan inverse of 0.5 over 3.5. Now that gives me something like 81.86989 degrees. So to three significant figures, we'll give that as 81.9 degrees. I'll just put three significant figures. Example 17. The L-shaped lamina in example 16, which I've got here, has mass m. Find the angle that Fe makes with the vertical when a mass of 1/10 m is attached to B and the lamina is freely suspended from F. So basically what we're doing is we're clumping this whole lamina together. We know its center of mass and giving it of mass m, and then we're adding another mass of 1/10 m at this point. So we're now going to do a table to work out the new center of mass of this lamina and the attached mass. So we'll start with the lamina that we worked out before. We've now got a mass of m, and its center of mass from memory was x is 1.5 and y is 2.5. And then we've got this new mass of mass 1/10 m, and I can see that that's at the point 4, 0. So 4 for x, 0 for y. And now I do my calculation to work out x bar and y bar. So x bar will be 1.5, or sorry, m times by 1.5. So 1.5 m plus 4 times by 1/10 m. So that's 4 over 10 m divided by the total mass, which is going to be 11 over 10, 1/10 plus 1 m. That gives 19 over 11 as all the m's cancel out. And then we'll work out y bar. So that will be 2.5 times by m plus 0 times by 1/10 m. Don't really need to write it down, I'll put it in, divided by the total mass, which again is 11 over 10 m. The m's will cancel out, and that gives us 25 over 11. Okay, so if I work out roughly what these are as decimals, it'll give me some rough idea where to put it on this diagram. Okay, so I can see that I need to go about 1.7 across and 2.3 up. So I'll put my center of mass here, G, and I'll just give it a coordinate, which is 19 over 11, 25 over 11. And this lamina is being freely suspended by F. So our line goes through F to the center of mass, and this now becomes the vertical, and I want to find the angle between this purple line, the vertical, and the side FE. So this is the angle here that I want to find. Now I can draw a right angle triangle and work out the lengths of the sides that I need. Okay, so this side here, well, that's just going to be the same as this length here, which is 19 over 11. It might be useful maybe just to put some dotted lines like this to see the lengths that I've got. So that's 19 over 11. This is 25 over 11 from the bottom up to there. So that means that this length up here is going to be 19 over 11. Then to find this side here, well, I know this is 25 over 11 up to here. The whole side is 6. So if I do 6 minus 25 over 11, I'm going to get the length of this side, which is opposite to the angle I want to find. And that gives me 41 over 11. Right, so that angle that I want to find, the angle that it makes with the vertical, is going to be the tan inverse of 41 over 11 divided by 19 over 11. That gives me 65.13630343 degrees. So again, three significant figures. So I'll do 65.1 degrees. So that's the angle that the vertical there is making with the side FE. So make sure that you draw a clear diagram and you clearly work out the lengths of those sides, because it's easy to use the values you've already written down for the centre of mass. Be careful to get the right lengths. So you should now be able to complete exercise 2F on pages 61 to 64 of the textbook.